Good holy everyone, I am unique number 19, Iron Joy H. Fernandez, and I am your teacher for the next topic. Earlier, you learned about how to perform a hypothesis test for a population mean. Now, in this part of the lesson, we are going to learn about testing hypothesis per proportions, variance, and standard deviations. Let's start with hypothesis test per proportions. Hypothesis tests per proportions can be used when politicians want to know the proportions of their constituents who favor a certain bill, or when quality assurance engineers test the proportion of parts that are defective. When you perform a hypothesis test of a single population proportion, you take a simple random sample from the population. You must meet the conditions for a binomial distributions, which are: there are a certain number of independent trials. The outcome of any trial are success or failure, and each trial has the same probability of a success P. The shape of the binomial distribution needs to be similar to the shape of the normal distribution. To ensure this, the quantities NP and NQ must both be greater than 5. Then the binomial distribution of a sample proportion can be approximated by the normal distribution with mu equals P, and the standard error is sigma sub P hat equals the square root of P times Q all over N. In conducting a hypothesis testing for one sample proportion, we need to follow the following steps. Step 1. Verify that the sampling distribution of P hat can be approximated by a normal distribution. We have NP greater than or equal to 5 and NQ, or N times Q, greater than or equal to 5. Step 2. State the claim mathematically and verbally. Identify the null and alternative hypothesis. Step 3. Specify the level of significance denoted by alpha, then determine the critical values and the rejection region. In this step, we can use the standard normal distribution table to find the critical value. And step 4. Find the standardized test statistic using the formula Z equals P hat minus P all over the square root of P times Q all over N, and sketch the sampling distribution. And step 5, make a decision to reject or fail to reject the null hypothesis. If Z is in the rejection region, then reject the null hypothesis. Otherwise, fail to reject the null hypothesis. And finally, for step 6, interpret the decision in the context of the original claim. Now that we knew the steps in conducting the hypothesis testing for one sample proportion, let's try to solve this example. A researcher claims that less than 40% of US cell phone owners use their phone for most of their online browsing. In a random sample of 100 adults, 31% say they use their phone for most of their online browsing. At a level of significance 0.01, is there enough evidence to support the researcher's claim? Step 1. In this example, we have N times P, which is equal to 100 times 0.40 equals 40, and N times Q equals 100 times 0.60 equals 60. The product of NP and NQ are both greater than 5. We satisfy the normality condition, so in this case, we can use a z-test. Let's proceed to step 2. Step 2, identify the null and alternative hypothesis. The claim is less than 40% use their phone for most of their online browsing. So, the alternative hypothesis is P less than 0.4, which is the claim, and the null hypothesis is P greater than or equal to 0.4. Step 3 is to find the level of significance and determine the critical values and the rejection region. In this example, the level of significance is 0.01. Because the test is left-tailed and the level of significance is 0.01, using the z-table, the nearest value to the significance level is negative 2.33. So, our critical value is negative 2.33, and our rejection region is Z less than negative 2.33. Step 4 is to find the standardized test statistics and sketch the sampling distribution. Our formula is z is equal to p hat minus p all over the square root of p times q all over n. By performing the formula, we get negative 1.84. Now, once again, our p hat is taken from the 31% of the adult who say they use their phone for most of their online browsing divided by the random sample of 100 adults. So we have 31 divided by 100 gives us 0.31. Again, our z is equal to negative 1.84. The next step is to sketch the value of the standardized test statistic z. Because z is not in the rejection region, we fail to reject the null hypothesis. Now, for step 5, which is our conclusion, we say, with a z value of negative 1.84, which is greater than the critical value of negative 2.33, we fail to reject the null hypothesis, which makes our test not significant. Therefore, there is not enough evidence at the level of 1% significance to support the claim that less than 40% of US cell phone owners use their phones for most of their online browsing. That ends our lesson for the hypothesis testing for proportions. And now let's proceed to the next part, which is the hypothesis testing for variance or standard deviation. To test a variance or a standard deviation of a population that is normally distributed, we can use the Chisquared Test. The Chisquared Test for a variance or standard deviation is not as robust as the test for the population mean or the population proportion. So it is essential in performing a Chisquared Test for a variance or standard deviation that the population be normally distributed. The result can be misleading when the population is not normal. For a normally distributed population, we can test the variance and the standard deviation of the process using the chi-square distribution with n-1 degrees of freedom. But before learning how to do the test, we must know first how to find the critical values as shown in the guidelines. In finding the critical values for a chi-square test, first, specify the level of significance denoted as an alpha symbol. Then, identify the degrees of freedom, which is df equals n-1. Next, use a chi-square distribution table to find the critical values. This is the example of the chi-square distribution table. For a right-tilde test, use the value that corresponds to the degrees of freedom and the level of significance. For example, find the critical value for a right-tilde test when n is equal to 26 and alpha or level of significance is 0.10. In this case, our degrees of freedom is equal to n-1 equals 26 minus 1, which gives 25, and our level of significance is 0.10. Now, use these two values, the degrees of freedom and the level of significance, to find the critical value using the chi-square distribution table. And our critical value is 34.382. Now, what if the test is left-tailed? For a left-tailed test, use the value that corresponds to the degrees of freedom and 1 minus the level of significance. For example, find the critical value for a left-tailed test when n is equal to 11 and the level of significance is 0.01. In this example, the degrees of freedom is 11 minus 1 equals 10. Since it is a left-tailed, we subtract the level of significance from 1, so we have 1 minus the level of significance 0.01 equals 0.99. In chi-square distribution table with the degrees of freedom which is equal to 10 and the area of 0.99, the critical value is 2.558. The third example is a two-tailed test. For two-tailed tests, use the values that corresponds to the degrees of freedom and 1/2 of the level of significance for the left tail. And for the right tail, we use the degrees of freedom and 1 minus 1/2 of the level of significance. For example, find the critical values for a two-tailed test when n is equal to 9 and the level of significance is 0.05. In this example, the degrees of freedom are n minus 1 equals 9 minus 1 equals 8. The figure below shows a chi-square distribution with 8 degrees of freedom and a shaded area of 1/2 of the level of significance, which is equal to 0.025 in each tail. So the areas of the critical values are 0.025 in each tail. In chi-square distribution table, with the degrees of freedom 8 and the areas 0.025 and 0.975, the critical values are 2.180 and 17.535. Now that we knew how to find the critical values for a chi-square test, let's proceed to the testing of hypothesis using chi-square test for a variance or standard deviation. The chi-square test for a variance or standard deviation is a statistical test for a population variance or a standard deviation. The chi-square test can only be used when the population is normal. The test statistics is S squared and the standardized test statistics is X squared equals the quantity of n minus 1 closed quantity times S squared all divided by the sigma squared. We will use this formula to test the hypothesis of variance or standard deviation. In using a chi-square test, we also need to follow certain steps. First, verify that the sample is random and the population is normally distributed. It is important to know that the given population is normally distributed so that we can use the chi-square test. Second, state the claim and identify the null and alternative hypothesis. Third, specify the level of significance and identify the degrees of freedom. In step 3, after specifying the degrees of freedom and the level of significance, use these values to find the critical value using the chi-square distribution table. For the next step, step 4, determine the critical value and the rejection region. After that, in step 5, find the standardized test statistics using the formula X squared equals the quantity of n minus 1 closed quantity times S squared all divided by the sigma squared and sketch the sampling distribution. And finally, make a decision to reject or fail to reject the null hypothesis. If X squared is in the rejection region, then reject the null hypothesis. Otherwise, fail to reject the null hypothesis. As a conclusion, interpret the decision in the context of the original claim. Now that we knew the guidelines in using the chi-square test for a variance or standard deviation, let's try to solve this problem. A dairy processing company claims that the variance of the amount of fat in the whole milk processed by the company is no more than 0.25. You suspect this is wrong and find that a random sample of 41 milk containers has a variance of 0.27. At a level of significance of 0.05, is there enough evidence to reject the company's claim? Assume the population is normally distributed. In this example, we use a hypothesis test for the population variance. Step 1. Because the sample is random and the population is normally distributed, we can use the chi-square test. Step 2. State the claim and identify the null and alternative hypothesis. The claim is the variance is no more than 0.25. So the null hypothesis is S squared less than or equal to 0.25, which is the claim, and the alternative hypothesis is S squared greater than 0.25. In step 3, since our alternative hypothesis is using a greater than sign, our test is a right-tailed test. The level of significance is 0.05 and the degrees of freedom are df equals 41 minus 1 is equal to 40. So for this step, use the level of significance which is 0.05 and the degrees of freedom which is 40 to get the critical values using the chi-square distribution table. So our critical value is 55.758. And using the normal distribution or graph, our rejection region is located here. After that, in step 5, find the standardized test statistics, which is x squared equals the quantity of n minus 1 closed quantity times s squared all over sigma squared. Now, let us solve for our standardized test statistics. We have x squared equals n, which is 41 minus 1 closed quantity multiplied by s squared, which is 0.27 all over the sigma squared or 0.25. By performing the operations, we get 43.2. Finally, decide to reject or fail to reject the null hypothesis. In this case, because our x is 43.2, which is not in the rejection region, we fail to reject the null hypothesis. And for the last part, which is our conclusion, we can say that with the x squared value of 43.2, which is not in the rejection region, we fail to reject the null hypothesis. This makes our test not significant. Therefore, there is not enough evidence at the level of 5% significance to reject the company's claim that the variance of the amount of fat in the whole milk is no more than 0.25. We're done with the hypothesis test for the population variance. Now let's have another example using the hypothesis test for the standard deviation. The problem is, a company claims that the standard deviation of the length of time it takes an incoming telephone call to be transferred to the correct office is less than 1.4 minutes. A random sample of 25 incoming telephone calls has a standard deviation of 1.1 minutes. At a level of significance of 0.10, is there enough evidence to support the company's claim? Assume the population is normally distributed. For the step 1, it is indicated in the problem that the population is normally distributed. So in this case, we can use the chi-square test. For the next step, step 2, state the claim and identify the null and alternative hypothesis. In this example, the claim is the standard deviation is less than 1.4 minutes. So the alternative hypothesis is less than 1.4, which is the claim, and the null hypothesis is greater than or equal to 1.4. For our step 3, since our alternative hypothesis is using a less than sign, our test is a left-tailed test. So our level of significance is 0.10 and the degrees of freedom are 25 minus 1 equals 24. So for step 4, use the level of significance which is 0.10 and the degrees of freedom which is 24 to get the critical value using the chi-square distribution table. So using the table, our critical value is 15.659. Now, let's locate our rejection region. Using the normal distribution and the critical value of 15.659, our rejection region is located here. After that, in step 5, let's solve for the standardized test statistics, which is x squared equals the quantity of n minus 1 closed quantity multiplied by s squared all over sigma squared, and sketch the sampling distribution. For our x squared, we have the quantity of n minus 1 or 25 minus 1 closed quantity multiplied by s squared or 1.1 squared all over sigma squared or 1.4 squared. By performing the operations, we get 14.816. Now, let's locate the value of x squared, which is 14.816. Using the normal distribution or the graph, our x squared, which is 14.816, is located in the rejection region. Now, we need to decide to reject or to fail to reject the null hypothesis. Because our x squared, which is 14.816, is in the rejection region, we decide to reject the null hypothesis. For the last step, which is our conclusion, we can say that with the x squared value of 14.816, which is in the rejection region, we decide to reject the null hypothesis. This makes our test significant. Therefore, there is enough evidence at the 10% level of significance to support the claim that the standard deviation of the length of time it takes an incoming call to be transferred to the correct office is less than 1.4 minutes. That ends my discussion. I hope that you learned something out of this video. I am unique number 19, Iron Joy H. Fernandez. Now let's proceed to the next topic, testing hypothesis with two samples, which will be discussed by Sir Jasser John Arsenal and Ma'am Hayden Bantilan.